Now let's talk about question 4.18. So the first thing you always want to do is draw your control volume. So I'm going to draw in the shower head. Okay. And then I'm going to use a dotted line to indicate my control volume. And the control volume is just indicated before the actual wall of the pipe begins. All right. The next thing you want to do is fill in your normal and velocity vectors. So I know that my normal vectors are always perpendicular to the control volume and away from the control volume. So here we are perpendicular to and away from the control volume. I also know that my velocity is entering here, so V1 points inwards, right? I then have something exiting here, so my normal vector points away from and perpendicular to the control volume, and my velocity is exiting, so it points outwards. At the bottom, I know that my normal must point perpendicular to and away from the control volume, and I also know that my velocity is exiting. Alright, now that we fill that in, the next thing we need to do is indicate our assumptions. We are going to assume that the fluid is incompressible. Now, if the fluid is incompressible, it means that you cannot have accumulation, which means there is no change with respect to time, which means that you are operating at steady state. So once we've got all those implications down, I'm just going to write it. Assume incompressible. Well, it's actually water, so I'm going to say assume water as incompressible, which implies steady state. Now, the good thing about this is that when you write out the continuity equation, which is the double integral, okay, the good thing about steady state means that this term can disappear entirely. So the only thing left for us to do now is to simply fill in this term. So let's begin doing that. So I'm going to leave everything as variables for now and substitute in numbers later. It makes it a bit easier to calculate and we don't have to carry so many decimals. All right, so we're dealing with density of water multiplied by V1 multiplied by N1. Now remember, if you want to convert N1 into a number, you simply need to say cos of the angle between the normal vector and the velocity vector. So the angle between the normal vector and the velocity vector is 180 degrees. So you'll say cos of 180 degrees. All right, and multiplied by area 1 plus density rho 2. Remember the normal vector now, the angle between the normal vector and the velocity vector is 0 degrees. So you can say cos of 0 degrees multiplied by area 2. The thing to note here is that area 1 is the same as area 2. Because if you go up here, area 1 and area 2, the pipe is of the same thickness throughout. So I'm actually just going to label this as area 1 for now. All right. And to that, I'm going to add density, velocity 3, normal 3, the angle between the normal and the velocity, cos of 0 degrees, multiplied by area 3. All of that is going to equal to 0. All right, now I'm going to rearrange the equation and move everything over so that it makes a bit more sense and so that I can cancel some things out. Okay, so this is A2, but I'm going to label it as A1 because they have the same area. Okay, so now that I've filled in everything, let's see. We can divide throughout on both sides by rho and cancel them out. And I'm left with V3 times A3 equals V1 times A1 minus V2 times A1. You can see there's a common A1 on this side. So I'm going to pull that out. That's equal to V3. And I'm going to divide here by A3. The reason we solve for V3 is because that is what we want to know from the question. The question is asking us, what is the exit velocity from the shower jets? So V3 represents the velocity from the shower jets. All right, so now we can start working things out. Velocity 1, you'll see, is given to us not as a velocity, but as a volumetric flow rate. So I put the dot there to indicate that this is a volumetric flow rate and not a velocity. All right, so a volumetric flow rate is 0.0013 0.0013 cubic meter per second. Now remember, volumetric flow rate is equal to velocity multiplied by area. Right? If you want to check, you can do a dimensional analysis. Velocity is meter per second, area is square meters. If you multiply them out, you get cubic meter per second. All right. So if I want to find V1, then all I have to do is take volumetric flow rate, 0.0013, divided by the area 1, which is pi over 4, multiplied by diameter 1 squared, which is 0.02 squared, and I get 4.138 meter per second. So we've already got V1. Let's see V2. That is given to us as 2.1 meter per second. So in the equation above, we have V1, we have V2. Let's find A1 and A3. A1 is equal to pi over 4 multiplied by 0.02 squared, which is 3.142 times 10 to the minus 4 meter squared. And if we want to work out area 3, you must remember that area 3 is equal to 100 multiplied by the area of one shower hole, because there are 100 shower holes, so we'll multiply the area by 100. So the area of one shower hole is pi over 4 multiplied by 1 millimeter squared. So 1 millimeter can also be written as 1 times 10 to the minus 3 squared. Pi over 4d squared multiplied by 100. And that should give me 7.854 times 10 to the minus 5 square meters. So if I put all of this, A1, A3, V2, and V1, into this equation above, I should get the answer I'm looking for. Let's go. V3 is equal to A1 divided by A3, 3.142 times 10 to the minus 4, divided by 7.854 times 10 to the minus 5. V1 minus 2.1. And the answer I get out is 8.15 meter per second. And that's it. I hope you found this helpful.